In this video, I'm going to be looking at sound waves and explaining what beats in the Doppler effect is associated with sound. In my previous video, I've looked at intensity, reflection, diffraction of sound waves, and echolocation. So please check that out in 3K in this Waves and Thermodynamics playlist. If you already have it, please subscribe. So let's have a look at beats. A beat is the interference pattern between two sounds of slightly different frequencies, and this is detected as a periodic vibration in volume, having a period equal to the difference between the frequencies of the component waves. And you can see that easily in the diagram here, where you've got a blue wave in frequency 1 or wave 1, and you've got the red wave of frequency 2. They're slightly out of phase, where F1 is slightly greater than F2, so the blue is greater than the red. When they're combined, there's an in-phase and out-phase component, and when the amplitudes are combined, you've got a loud sound and a soft sound. Okay, you can see that in the diagram. So that's a beat. What is a Doppler effect? You may have learned it in junior science. It's basically a phenomenon that you may hear every day with an ambulance or a police car driving past you. But the Doppler effect is a phenomenon of waves that is observed when there's relative motion between the source of the waves and the observer. So it causes an apparent increase in frequency when it's moving towards you, and a decrease in frequency when it's moving away from you. And you can work this out mathematically by the equation given to you there. Okay, let's have a look at a question here about beats. So consider the diagram below, which represents two sound waves, A and B. And if each sound wave represents 0.1 seconds of time, enter A, B, and C. If you'd like the opportunity to pause the video now to do this before I answer it. Okay, let's have a look here. You should see the green font appear. So when you count the wavelengths for A, you got 33.5 in 0.1 seconds. Divide 33.5 divided by 0.1 seconds, and the frequency is 335 Hertz. Do the same for B and you'll get 305 Hertz. So beats equals F2 minus F1, and the frequency is 30 Hertz. Alright, let's have a look at a question now on the Doppler effect. Consider the diagram which shows the sound waves produced by the source of a sound moving towards the left. Justify all your answers below for A to E. If you like the opportunity now to pause the video, then do so. Alright, let's have a look at each of those answers. So for A, which observer will hear the sound of the same frequency as the source? And there'll be the one directly in line below that or above that, but the only option we have is observer 3. B, compare the frequency of the sound heard by observer 3, that of observer 1. Now, 1 is going to hear less frequency, or it's going to have less frequency because it's moving away from it than observer 3. So 3 will have a higher frequency than 1. C, compare the frequency of sound heard by the observer 3 to that of observer 2. Now, observer 2 slightly hears a lower frequency than 3 because it's behind the source and the waves are spreading out or decreasing. Okay, so the frequency is decreasing compared to 3 because it's behind 3. Alright, slightly better than observer 1. Okay, so let's have a look at D. Compare the frequency of the sound heard by observer 4 to that of heard by observer 5. So observer 4 hears a higher frequency because the source is moving directly towards it, but the only component of the forwards motion is towards observer 5. Okay, now for E, compare the frequency of the sound heard from observer 5 to 1. Observer 5 hears a higher frequency because it's moving towards 5 and moving away from 1. So it will have a higher frequency for 5 than 1. Okay, let's have a look at another question here. A stationary submarine emits a frequency of 600 cycles per second and receives an echo from a second submarine at 608 cycles per second. If the speed of sound in the water is 1530 meters per second, how fast is the second submarine and moving in what direction? If you like the opportunity to pause it now, this is a Doppler effect question. Okay, let's have a look here now. You should see font in green and working out. So the source is stationary and the observed frequency is high, therefore the second submarine is moving towards it. Okay. Now let's have a look at the mathematics. So you got the F receiver equals F source. In brackets, you got the V velocity of the wave plus the velocity of the receiver divided by the velocity of the wave. So you got 600 equals 608, equals 600 brackets 1530 plus V close brackets, divided by 1530. Now you need to move the 1530 at the bottom to the left hand side, so you times it by 1530, so 608 times 1530 equals 930,240 on the left hand side, equals 600 times 1530 gives you 918,000 times 600V. Now you need to minus the 918,000 to the left hand side, and you'll get 600V alone on the right hand side. Now when you minus those two large numbers together, you'll get 12,240 equals 600V. Now to get rid of the 600V to find the velocity, you divide it by 600 on both sides, and you'll get your answer as 20.4 meters per second. I hope you enjoyed watching this video. It did take me a very long time in incorporating this large dot point with beats and Doppler effect. I hope it makes it clear. If it doesn't, leave a comment, like or dislike, and give me some feedback. Please subscribe to my channel. Any feedback's positive feedback for me to produce my next Module 4 playlist on electricity and magnetism for this Year 11 course. So thank you for your time.